So first I'm going to give a quick introduction to Prolog and a bit of a demonstration on how the syntax and semantics of the programming language work. Prolog, which is actually short for programming logic, was one of the earliest logic-based programming languages and remains today still one of the most used and most popular logic-based languages. It's mostly associated with two main areas of computer science, which, as you can see, are number one, computational linguistics, which is like taking a natural spoken language and converting it to code so that it can be used in programs and applications. And then number two, which is what this project will be more focused at looking at, which is artificial intelligence. So Prolog is based in first order or predicate logic, which means that the logic is expressed in terms of relationships of objects, means it's called a declarative language, which is actually unlike most other programming languages. So in learning to code Prolog, it's actually very simple language, but there's just three main concepts to learn, which is number one, facts, number two, rules, and number three, queries. And so I'm going to take a little bit of a deeper look at all three of these concepts. So first off, I'm going to look at what facts are. So a fact is just a relationship of the single data type in Prolog called a term onto other terms or onto themselves. So just like it sounds, it's something that is known to be true. It is written as a relationship or the predicate, and then in parentheses the term separated by commas and ending with period. So I'm just going to do a quick example, such as happy, which is the predicate, and then the term that's acting on, we can say Jim is. So this is read as Jim is happy, and then we can repeat the relationship with anyone like Sarah or happy, ABC. Okay, so happy is the predicate, and then Jim or Sarah or ABC is the term here. So there are couple different types of term in Prolog. In this example, Jim, Sarah, and ABC are all called atoms. An atom is just a general name with no inherent meaning, such as any of these, or it could also be something in single quotes like random name. So yeah, atoms always start with a lowercase letter or the single quotes. Like some more examples of facts with atoms are female Sarah or university SLU Madrid. And you always want to separate your lines of code by predicate just to maintain proper code style. Okay, so these are all examples of rules with facts with atoms, and then I'm going to go on to the next data type of the type of term, which are called numbers. So numbers can either be floats or integers. So some examples of facts with numbers are like number pets 5, or for example, you could have grade for like a class or something 88.00. So the next type of term that we're going to look at in Prolog is called a compound term. A compound term is made up of an atom called the functor, and then in parentheses a number of arguments, which are just more terms. So this fact is actually an example of a compound term, but it just has one argument on the inside. So the functor here would be grade, and number of pets, university, and so on. So here our fact is going to be called parent of, and we're going to say Tom, Grace, or we'll continue with Jim and Sarah. So this is read as Jim is the parent of Sarah. So this compound term has two arguments on the inside, which is known as the arity, is the number of arguments. So parent of, this fact has an arity of 2, grade has an arity of 1. Just a single atom, such as Jim or Sarah, those have arity of 0. So a compound term is really any term, but typically we recognize it when it has two or more arguments on the inside of the parentheses. Okay, so these are our facts, things that we know to be true. The next thing that we have to look at, like if we go back to the intro to Prolog, the next main concept is something called a rule. So a rule is when the truth of one fact depends on another single or group of facts to recognize if the original fact is true. So they usually take the form of an if statement, represented by a specific symbol. I'm going to show you in a sec. So this example of rule is sings Jim. So Jim sings if and always happy Jim. So this is read as Jim sings if, marked by this symbol in the middle, Jim is happy. So as we know, as we can see up top, Jim is happy, so Jim sings would be true in this case. So that should be a period at the end. Another rule we can write, we'll be using a final type of term in Prolog called a variable. So we're going to write it as toddler A. So A is a toddler if age A is 3. So 3 is the age of A. Okay, so A here is a variable, which is a string of letters starting with a capital letter or a underscore, and it can be any broad person. It doesn't necessarily represent any specific thing or term. So in this case, if I had a bunch of people, like Sarah and Jim, had marked their different ages, any one of those terms whose age is 3 is a toddler. Another example could be son of. So X is the son of Y if parent of Y is the parent of, has to be capital Y. Y is the parent of X, and represented by a comma here instead of a period, male. X is male. So this reads as X is the son of Y if Y is the parent of X and X is male. Now we could have another corresponding rule called daughter of, which X is the daughter of Y if Y is the parent of X and female. X is female. So these are rules which use the truth of certain facts in the past to determine the truth of the facts on the left side of the if statement as seen here. So next I'm going to show you the final main part of the syntax and semantics of Prolog called queries. So queries are basically asking the application questions to see based on your database, which is this set of rules and facts. Basically ask the application about the truth of certain statements, and it will check your database to see whether or not that statement is true or false, or can do some other cool things as well. So I will show you that with a separate set of facts and rules. So coding in Prolog takes two different things of software. On the left, as I mentioned before, we have the database, and the database is usually just a text editor with where all the facts and rules are stored, and then once we save that, we upload it to the programming environment or the IDE on the right here. We're using SWI Prolog, where the file is uploaded, and then we can compile it and run queries, which are basically like questions we're asking the compiler. So first things first, we're going to finishing writing some some rules in the database. So we're going to run a program to see who is the son or daughter of which people. So as you can see, we have some different people as male. Tom is male, Jack is male, Chuck is male, and then female, Sally is female, Grace is female, Sarah is female. And then we have a little bit of a family tree thing going on where Tom is the parent of Jack, and Tom is the parent of Grace, and then Chuck is the parent of Sally, and Sarah is the parent of Chuck. So the final two rules we're going to write here are son of X is the son of Y if parent of Y is the parent of X and male X. And then on the opposite side, we have daughter of X is the daughter of Y if parent of Y is the parent of X and X is female. Okay, so we're going to save that and then come over to the IDE and upload it like this. Open bracket, quote, the destination of the file. We have it saved as Prolog demo.pl, which is the Prolog file name. Close bracket, period. True. So this is a sign that we have the database successfully uploaded to the IDE. Okay, so here's some cool things we can do. First, we can just check, like, male, Tom is male. True. We can check Tom is female, and it will give us a false. So that's just a good check that the database is successfully uploaded. You can also do some other stuff like testing with variables, such as X is male. If I send that, it will show you all the possible solutions of X. After X is Tom, I just put a semicolon, and we'll go through Jack, Chuck, and then once the period comes up, you know that that's the end of the list. We can also do it for compound terms like parent of, where parent of Y. So here it's going to show us all the people or answers for Y that Tom is the parent of. So we have Y equals Jack and semicolon, Y equals Grace. So these are both examples. All of these are examples of queries. Like anywhere after the question mark, it's basically a question that you're asking the application, and it spits out the correct answer for possibilities of Y or possibilities of X or true or false. Those are the main different solutions to the queries in this example. So we want to see who is the son and who is the daughter of based on our rules. So one way we can do it is just like we showed with variables. Son of X is Y, period. And this will just basically go through and show us all the parent-son combinations. So Jack is the son of Tom. Chuck is the son of Sarah. So if we go back to our database on the left, this makes sense because parent of Tom is the parent of Jack, and then Jack is male, Sarah is the parent of Chuck, and Chuck is male. We can do the same thing with daughter, but this time we're just going to check for stuff being true or false. Daughter of, let's see, Jack is the daughter of Tom. False, because like we just said, Jack is male. But if we do daughter of, Grace is the daughter of Tom, here we'll get a truth. So that's basically it. Some of the cool stuff you can do with Prolog, using facts and rules, and then completing queries on those facts and rules for getting answers from the application. Some of the default libraries used in Prolog when programming some of the basic functions that we found most useful, most commonly used when programming in this language. So as Prolog is a declarative language based on predicates rather than libraries of functions or methods, Prolog libraries contain predicates for the programmer to use. So built-in predicates and library predicates seem very similar, as most IDEs for Prolog already automatically load many of the libraries most popularly used. However, some still must be loaded manually through something like an import function or the use module function, which just is use module and then in parentheses the library name. So also something to note is that predicates for Prolog in general are denoted by the format of the predicate name followed by a slash and then an integer, such as append2 or append3, as you can see here on the slide. So that number just represents the number of arguments that the predicate can take. So this is something to look out for in the following slides, as it can look kind of confusing, but that just shows that sometimes there are different variations of the same function, and those have to be represented with the slash number. So library predicates can also be user defined, while that's not possible for the built-in functions. If you try to redefine a built-in predicate, this will result in a permissions error from the compiler. So in some senses that hurts the writability, but still maintains good reliability for Prolog. So we're going to just explore some of the uses and the functions of the following libraries. First up, we're just going to discuss some of the built-in predicates that are very useful, especially in the code that we wrote for our application, but also just in general. So the first predicate we're going to look at is called write, and that's just used as in every programming language there is, that like hello world. Write is used to just print the given term to the output, or there's a different type of write, as you can see, write to, which you can also, this two arguments are the term that you're trying to output, and also you can select a particular stream that you'd like to output the function to, or output the term to. So the next one is format, and format is a family of predicates that are extremely useful and versatile in producing text. So typically, format can take two arguments, where the first is a rule or a list of formatting rules, and then followed by an argument or more arguments that are all those formatting rules are to be applied onto before this is then printed to the output stream. And then we have length, which length is used to see if the number of elements in a list matches the given integer. So we actually use this later on to see in our Sudoku Solver if the puzzle has 9 row elements, and if in each of those rows there's another 9 cell elements. So it's very useful in general programming. The first specific library we're going to look at is called library lists. This library is used for manipulating, which is extremely important in Prolog, as lists are one of the most common data structures used in the language. So lists are created with just 2 brackets with elements on the inside separated by commas. So almost every Prolog IDE automatically includes this library because of how important lists are. So as we saw, like length is a built-in predicate, but there's a lot more you can do with some of the predicates included in this library. So the first one is member/2. So this is just true, basically like a search for the member of a given list. Then there's the append predicates, append3 or append2. So append/3 is used to concatenate list 1 and list 2 into a new third list, list 3. And then append/2 can, if you have a list of lists, those can all be concatenated into just one list, which can be extremely important and save a lot of time. The next predicate is select. So select is true if list 1 is the same as list 2, except for the selected element. So basically, if list 1 minus the selected element is equal to list 2, then select will return true. Next is same length, which is just true if list 1 and 2 have the same number of elements. And then some arithmetic predicates, max member and min member. These are good just to find the minimum or maximum of a list, which can be useful for certain sorting and searching algorithms. And finally, sum is it just produces a result, which is the sum of all the numbers in the list. The next library we're going to look at is called library apply. Library apply is a Prolog library used to apply predicates to all of the elements or just certain elements of a list. So this is another really helpful list manipulating library that saves a lot of time for the programmer. So some of the predicates include include and exclude. So include filters for a list of elements which a given goal succeeds. So you can just look for certain elements that meet a goal, or exclude is the opposite of that. So the same as negating include, where it filters for elements on which the goal fails. The next one is partition, which is actually very similar to include and exclude. So this filters a list of elements for those that a given predicate. So for all the elements that a predicate is true onto, it has filters for those elements separated by those that the predicate excludes. So rather than just giving the includes or the excludes, it gives the includes first and then the excludes second. So that's why it's kind of like a partition in between the two. Then the third one is map list. So map list returns true if a given goal can be applied to every single element of the list. So it's kind of like include in that sense, but it's true if include applies to all of the elements. It can be used to look at a single list or either pairs from 2 lists or triplets from 3 lists or quadruplets for up to 4 lists at a time. Then the final basic library that we're going to look at is called library random, which is a library used to generate random numbers, which can be useful in endless scenarios, especially with randomization and probabilities. This can also be used in a more complex setting for like combinatorial problems, which Damien's going to talk a little bit about for artificial intelligence. But this has so many uses in just everyday programming. So the first one, random R, which is actually an output which you get. So random produces a random float in just the open interval, which means not including the endpoints of 0.0 to 1.0. So basically just it's basically a random number which you can use for anything pretty much in there. Or if you want to be more specific, there's another version of random which has 3 arguments, L being the lower endpoint, U being the upper endpoint, and R being that output float. So you can either use integers or floats here, and depending on what you use as the endpoints, this will produce a random number R of that same given type. And then another 2 really helpful functions are called maybe and another form of maybe p. So these are essentially like a coin flip. Just calling maybe will have an equal probability of success and equal probability of fail. Or if you want it to be like a weighted coin or weighted die, you can use maybe and p as a probability as the argument. So we'll have a probability p to succeed and a probability of 1 minus p to fail. So those are really the main libraries and predicates that we saw to be extremely useful in just very basic programming in Prolog. So more specifically to our project in artificial intelligence, next Damien will be discussing some more of those specifically useful libraries to our domain.
Before we talk about the specific libraries that are used in Prolog for projects in artificial intelligence, I first want to quickly discuss the types of problems in the domain of AI that Prolog is good at solving. So artificial intelligence, or more specifically weak artificial intelligence, contains within it two distinguished approaches: symbolic AI and statistical or computational AI. Symbolic artificial intelligence, or good old-fashioned artificial intelligence, as coined by John Hodgland in his 1985 book, Artificial Intelligence, is a collection of methods in AI research that are based on problems dealing with human-readable symbols, logic, and search. Programs within this subdomain formulate outputs based on symbol-represented inputs. Such inputs under this approach are definite and fall under certainty. Examples of applications of symbolic AI are rule-based expert systems, which use a network of production rules to connect symbols similarly to if-then statements, theorem provers, intelligent forms of search, constraint-based approaches, etc. The symbols used in symbolic AI are grounded with sensory perception. The system works with domain-specific knowledge to improve the state-space search. By contrast, when there is uncertainty involved with the input, programmers or researchers use statistical or computational artificial intelligence, which uses artificial neural networks. This approach is used in machine learning and data mining, and is at the focal point of much contemporary AI research. Symbolic artificial intelligence research has fallen out of popularity since the 1980s. Critics of symbolic AI have posited that the technique can only be used to solve toy problems that are not of much scientific interest and cannot be used to build complex, scaled-up AI software. However, understanding both approaches is still important. Google DeepMind's AlphaGo uses a combination of machine learning, statistical AI, and Monte Carlo tree search, which is symbolic AI. Prolog, which first appeared in 1972, is frequently associated with symbolic approaches to AI. Specifically, Prolog is great for automating planning tasks, scheduling tasks, and solving combinatorial problems. Planning tasks include Connect 4 or Oregon State's Escape from Zurich problem. Scheduling tasks include timetabling, which are used to generate student high school schedules, or generating sports tournaments, such as the social golfer problem, which generates golfer schedules such that no two golfers play in the same group more than once. It should be noted that planning and scheduling tasks can be solved in the same way that combinatorial tasks are, or can be expressed as combinatorial problems, as they are solved using combinatorial optimization or other iterative trial and error processes common in artificial intelligence. Combinatorics, a field of math used to solve combinatorial tasks, uses counting to obtain results. They count structures, check that these structures satisfy certain criteria, construct such structures, or find optimal structures. Combinatorial problems include the n-queens problem, which generates n number of queens on a chessboard such that none of them threaten another, or Sudoku puzzles, but there's more on that later. So the question remains, how can we use combinatorics in Prolog to complete symbolic AI tasks? The answer is called constraint logic programming. Constraint logic programming is constraint programming in a logic programming language. We already covered that Prolog is a logic programming language and briefly discussed what that means in terms of rules and facts, so I'm not going to elaborate on that here, but I will discuss constraint programming. In constraint programming, users declare the constraints on feasible solutions for a set of decision variables. As opposed to the common primitives of imperative programming languages, constraints do not specify how to execute towards a solution step by step. Rather, constraints specify the properties of the solution that's to be found. The user still needs to specify a method in which to solve these constraints. Two of the most popular and well-defined such methods are constraint propagation and backtracking through search. Prolog has some constraint logic programming abilities as is built in, such as greater than, equal to, unequal to, and less than. These comparative predicates are really limited, obviously. To introduce constraint logic programming as well as constraint propagation and backtracking into Prolog more effectively, we use the CLP, constraint logic programming, libraries written by Marcus Triska. Triska has written CLP libraries for Boolean variables, integers, rational numbers, and floating point numbers. Broadly speaking, these libraries introduce more constraints that we defined earlier on data types such that users can do more sophisticated arithmetic and comparisons on data types while maintaining efficiency. Here, I'm going to mostly discuss CLPFD, which deals with finite domains. This library has an equivalent CLPZ, with Z standing for integers. These two things are used interchangeably and are pretty much the same library. And the other libraries serve essentially the same purpose, but they deal with different data types. These two in particular are the most popular, CLPFD and CLPZ, and we use CLPFD in this project. So one of the most basic purposes of this library, CLPFD, is to make the built-in predicates about equivalence, greater than, unequal to, all those that I covered just a bit ago, more broad and work better with variables and inline arithmetic. Additionally, this library offers a way to get more information out of lists. For example, the ins predicate takes a list that contains integers and accepts the list, or returns true, if the integers within the list, the elements within the list, fall within a range of defined integers. The predicate all different and all distinct determine if a list input has elements that are all different or all distinct. The difference between these two methods are the type of propagation they perform. All different allows us to perform weak propagation, and all distinct allows us to perform constraint propagation, which is a combination of weak propagation and intelligent propagation. I'm going to discuss this idea further when we get to our code, but it is important to define the term. Constraint propagation is a technique used with problems of finite domain to reduce and narrow the domain by determining elements that are inconsistent with the defined constraints. The all-distinct predicate isn't the only way to perform constraint propagation, but it is only one such way. This library also allows us to do search and backtracking. Through the labeling predicate, a Prolog program can traverse a search tree using a variety of traversal methods. Using this technique, solutions can be found by traversing through the search tree and backtracking when the generated solution we get, using the labeling technique, no longer holds true for the given constraints. So when we get to our code, I'll explain how constraint propagation and the labeling technique in CLPFD can be used together to solve our problem. But before we do that, I want to quickly show a demonstration of the n-queens problem and how constraint propagation and the labeling technique that uses search and backtracking can be used together to help solve that problem much more efficiently. So here we're looking at the n-queens problem using intelligent search. And again, we're looking at the combination of constraint propagation and the labeling technique in CLPFD. As you can see, some squares are grayed out here once the first queen is placed. This is what constraint propagation is doing. Constraint propagation is eliminating certain squares from the domain, leaving the white squares for search. Search, compared to constraint propagation, takes more time, and so eliminating as much search as possible, or as much of the labeling technique as possible from our program, will mean it goes much faster. At the 4x4 scale, this isn't too important, and even at the 8x8 scale, it isn't too important, but once we get higher and higher up, especially if we're animating each step, eliminating as much search as possible is best, and constraint propagation narrows the domain of search, and in turn, eliminates much of the search we need, leaving it to constraint propagation, which is much faster. As you can see here, this is an animation of constraint propagation being done over a bigger square. When we compare it to a different technique without using constraint propagation and only the search technique alone, you can see that it goes much, much faster in comparison. So again, the combination of constraint propagation and this labeling technique that uses search means we get really good, fast results when compared to just using search. This is important when we get to our program because we can use labeling alone, but it's just not as fast as constraint propagation. And even though we're not necessarily needing speed with this small of a puzzle, it's important to think about the most efficient ways to solve these sorts of problems. So we'll probably get a better understanding of how these two methods and how the CLPFD library works in context with our code when we get there in a second. But I just want to exemplify how, with only these simple additions that this library provides, we are able to solve a plethora of problems within the AI domain quickly, efficiently, and pretty intuitively. So now let's start talking about our project and what we wanted to accomplish and how we got to our project, things like that. So because we're in the domain of AI in Prolog, we needed to find some combinatorial task or some symbolic AI problem. And there are a lot of puzzles and logic problems related to these, some of which have been mentioned, and queens, etc. And one of the ones we stumbled across that seemed really cool to solve was Sudoku puzzles. And solving a Sudoku puzzle seemed not too hard, not out of reach, but also a pretty nice challenge for us. So all of us are probably familiar with Sudoku puzzles and probably know the rules. They're in every newspaper. We've played them a few times. There are easy ones and hard ones. And the rules are pretty simple, so we probably know that already. But still, I want to define Sudoku puzzles pretty clearly so that when we get to programming, we can define these constraints, literally the constraints we talked about, and then apply different methods of constraint propagation and labeling and search so that we solve the puzzle according to the rules exactly. At this point, I think it would be appropriate to define a Latin square. A Latin square is an n by n array filled with n different symbols, each occurring exactly once in each row and exactly once in each column. Below are two examples of order 5 Latin squares, meaning they're 5 by 5 arrays and contain exactly 5 symbols, integers 1 through 5. A Sudoku puzzle is a version or a permutation of a Latin square of order 9. So it is a 9 by 9 array in which all rows and all columns are pairwise distinct and have only integers 1 through 9 and only one of each integer in the row or column. But there's also one other specification, and that is that each subsquare or each 3 by 3 square contained within the 9 by 9 square must also have only one of each integer 1 through 9, or be pairwise distinct with those integers. Here is an example of a completed Sudoku puzzle. It has integers 1 through 9 on that first row, as you can see pretty clearly, and it has integers 1 through 9 in that first subsquare, as you can see pretty clearly, and it also has one of each integer in every row, every column, and every subsquare. You can check it, it's there. So now we need to begin thinking about how to express a Sudoku Latin square in Prolog. We have 81 different elements we need to keep track of because it's a 9 by 9 grid. Programmatically, we know one of the best ways of expressing a two-dimensional array like this is through an array of an array, or in Prolog, a list of lists. This list of lists will within it contain 9 different lists. Each of those 9 lists represent rows, and each of those rows within them contain 9 different elements which represent the single squares or the integers that we're trying to solve for. So again, we have the list of lists which contains 9 lists within it, and each of those 9 lists are 9 elements long. Now that we have these definitions or constraints, let's apply them to Prolog and see what they look like there. The first thing we want to do is create a predicate. Let's call it the solver because it's just going to do our solving for us. And this predicate is going to hold true when all of the requirements that we just defined, those definitions, those constraints of a finished Sudoku puzzle are met. Now we also need an input for this predicate, and here we'll put that list of lists we just talked about. We'll call it rows as it represents a list of rows. Now, when we're using this solver to solve puzzles, we are going to put the puzzle itself in place of this rows thing, or we're going to use a puzzle as the input, obviously. Now, let's start defining constraints as we just talked about, such that when we run this predicate, it only holds true for exactly what a Sudoku puzzle needs to be. The first thing we need to do is check that the puzzle itself is 9 rows long. To do this, we're going to use the length predicate, which takes 2 inputs, one being the list, which is going to be our input rows, and the second being what we want to check it against, which is 9. So we want to check that the length of rows is 9. So we're going to use the sublists, or the lists contained within the bigger list, as input. And by checking that each of these lists all have a length of 9 or all have the same length as the number of rows which we just checked, we are effectively testing that we have 9 columns. The next thing we're going to want to do is check that every element within our input is some integer 1 through 9. So to do this, we're going to use the append predicate, which takes a list of lists and concatenates them into a single list. So essentially, it's taking a 2D list and turning it into a one-dimensional list. This makes it easier to check all of the elements of the list at once. To check these elements, we're going to use a predicate defined within the CLPFD library, which is very helpful. We're going to take that newly concatenated list and use the ins method to check that each element within the list is some integer 1 through 9. Next, we're going to want to check some requirements of Latin squares. First, we're going to check that every element within every row is pairwise distinct. In other words, they're all different symbols. They're 1 through 9, we already checked that, but now we have to make sure there are no two of the same integer. To do that, we're going to use the predicate within CLPFD, all distinct. This is a really important predicate, and we're going to sort of explain how this has to do with constraint propagation later. But essentially what it's doing is checking that every element within the row is distinct from one another. Pretty simple. Next, we're going to want to do the same thing, but with columns. We're going to want to check that every element within each column is pairwise distinct. To do that, we're going to use a pretty nice tool within CLPFD called transpose. Transpose basically takes a list of lists, or a two-dimensional list, and transposes that list such that when we first had them represented as rows, now we have each list within the lists represented as columns. Now that we have a list representing columns, just as we had a list representing rows, we're going to want to do the same thing we just did with rows to check that all elements within columns are pairwise distinct. And again, we're using the same method, using all distinct from CLPFD. Now, this next part's a little trickier. We have the requirements for a traditional Latin square, but we have to remember that we also need to make sure subsquares, all 9 subsquares, all 9 3x3 subsquares within the Sudoku puzzle are also pairwise distinct. So to do that, first we're going to name these subsquares, A, B, C, D, E, F, and G, H, I, each representing subsquares on the first row, A, B, C, second row, D, E, F, and the last row, G, H, I. We're going to have to define a predicate for these subsquares. Let's call it squares. And it takes 3 lists as input. If these lists are empty, the predicate holds. Now let's consider the case that the first list starts with 3 elements, and the second list starts with 3 elements, and the third list starts with 3 elements. In this case, all of these elements, A through I, represent one subsquare, every constraint, and so all of these elements must be pairwise distinct. We can't solve all Sudoku puzzles, so we use the same because we don't have any form of all distinct or labeling CLPFD, but we do have constraint propagation set up. So we can kind of see because we're analyzing these subsquares, going 3 rows at a time. Then we must also test that the next 2 subsquares. I could do this in the row command line or the query line itself. So I just want to do it here because it's to basically test that the remaining subsquares within the row also are pairwise distinct. Now we have to define all of the required constraints of a Sudoku puzzle. Because we have now defined every constraint for a Sudoku solution, we can't solve all Sudoku puzzles because we don't have any form of search or labeling, but we do have constraint propagation set up. So we can kind of see how that looks like by running a sample query. But before we do that, I first want to write out a sample puzzle. I could do this in the command line or the query line itself, but I just want to do it here because it's easier to format and easier to see, and I can call back on it later. So here is our first sample puzzle. I just pulled this from the New York Times today. It is the hardest puzzle, and we're going to see what happens when we plug it in as a query to our solver. So here I am ready to start a query. The first thing I'm going to do is assign a puzzle to the variable rows. So we're going to take that puzzle we just wrote out and assign it to rows. And then we're going to call our predicate solver and use the puzzle as input. Next, I'm going to call the predicate map list again and use a clause, portray clause. This doesn't do anything functional with the program. All it does is allow us to view the output puzzle a little bit more clearly. And there it is. There's the solution. You can see here that we actually solved the whole puzzle with only constraint propagation. We haven't added any sort of labeling or search yet, but we were able to fill out the whole puzzle with only constraint propagation. This is possible with a lot of puzzles, and this is a hard puzzle on the New York Times, so it's kind of impressive actually, but it's not possible with all puzzles. Let's look at an example of a puzzle that we cannot solve with only constraint propagation. So here I have written another puzzle. I pulled this from the New York Times a few days ago, and it's also a hard puzzle. And the only difference here in terms of our program is that this one cannot be solved using only constraint propagation. So let's see what happens when we try to plug it into our program. We're going to use the same query here. We're just replacing the puzzle number, and let's see what happens. So you can see here, it's not fully filled in. It is partially filled in, so we do get some squares. For example, there is a 3 here that is not here. There is a 5 here that's not down here, and so on. And then we get a whole bunch of text here. And what this is saying is the square or the element at this memory, so these are just memory addresses with the underscore. The square at this memory can be 3 or 4 or 6 or 8, or it could be 5 or 6 or 1 or 5 or 7 at those 1 or 5 to 7, so 5, 6, or 7. It's basically saying, giving options for what those squares might be. So in this case, constraint propagation is narrowing the choices that the elements can be, but it cannot choose because we don't have any search method through the label. And what labeling does is it essentially just picks. It says, okay, for this memory address, we're just going to pick 7. And then it continues on doing constraint propagation or just more guesses. And once it gets to the point that it no longer works with the defined constraints we have, then it goes back. That's called backtracking. It goes back and then says, okay, let's try 8 here, and so on. And so essentially, while we can solve some problems with constraint propagation in Prolog using CLPFD, we cannot solve all problems. And to solve all problems, we have to use labeling. So right now we're looking at the New York Times hard puzzle, the first puzzle that we looked at that we solved only using constraint propagation. And I want to use this to describe exactly what constraint propagation does. So constraint propagation includes within it weak propagation and intelligent propagation. So I'm going to show you the difference between these two and what they mean. So to do that, I'm going to start filling this in just a little bit, and I have the answer in another window, so I'm just going to use that for reference. So if we go to auto candidate mode, we see here this square can only be 7. So essentially, what weak propagation does is at the beginning, if there's no clues, it assumes that all squares can be any number. With clues, it then eliminates numbers based on, okay, so if 4 here is here, then 4 cannot be in here. And so it essentially slowly eliminates numbers. What weak propagation does is it sees that when there's a point when there's only one possible solution, it knows that that's the answer, and so it fills it in. So in this example, 7 is the only possible solution here. So weak propagation knows that it has to be 7. It filled in just one more square here to demonstrate intelligent propagation, the second part of constraint propagation. So let's look at this column. This column has 3 missing squares. All of them could be 8. 2 of them could be 6. 1 of them could be 1. Weak propagation wouldn't see an answer here. But what intelligent propagation sees is that this square here is the only square in the column that can be 1. There's no other square here that can be 1. Even though it could be 8, it's the only one that can be 1, so then it must be 1. So constraint propagation is a really powerful tool that can be used to mostly solve these puzzles. Now, occasionally, this is where there's a point where search comes in. Now, again, this puzzle was solved using only constraint propagation, but as an example, sometimes the puzzle or the solver gets to the point where it has to make a choice. Basically, it sees this can be 8 or 6, or this can be 8 or 6, and it has to choose 1 to be 8 and 1 to be 6. So maybe it does this. And then it continues through search and constraint propagation along the path. If for some reason, if it gets to the point where it no longer works and maybe there is an 8 or a 6 here or something, it finds that that's the only place for a 6. Then it backtracks and says, okay, then maybe this is 6 and this is 8. And so combined with constraint propagation, search is a tool that can be used to solve every Sudoku puzzle, and it's really, really powerful. So I just want to show that our solver works and we solved this puzzle. Moving on, right now we're actually looking at the finished program. Here's the solver, and this was the main focus of our project, to solve Sudoku puzzles, and we're able to do that with constraint propagation and labeling, and it works great. So this is exactly what we set off to do. But when I was looking at the New York Times Sudoku puzzle website, they have easy, medium, and hard. They have 3 different difficulties for puzzles that you can solve, and it made me think, how exactly do they calculate this? How do they decide what puzzles are hard and what are easy? Because I assume they're computer generated, as that would be most efficient. So how do they determine the difficulty of a Sudoku puzzle? So we worked on how exactly to solve that problem, how to determine the difficulty. And the result here does sort of serve that purpose, but it also more serves another purpose, which is to show what weak propagation and constraint propagation can do and how far those things can get us. They don't get us all the way, weak propagation and constraint propagation, but they do get us some of the way, and I wanted to find a way to exemplify that. But at the same time, again, we are sort of measuring difficulty. So before I get into exactly what all this code means, let's run a sample query. So right now we're looking at the query screen, the interface, and we start off much the same way. We load up a puzzle, but instead of invoking the solver here, we invoke the difficulty predicate that we've added. And we have to add rows, which is our input, but also a bunch of variables, and we'll get into what those do and why those have to be there in a bit. But here's what it says. %solve from start. Using weak propagation, we get about 16% solved from the input to the solution. And I should mention, the intelligent propagation, I actually mean constraint propagation, so the combination of weak and intelligent. And so through constraint propagation, we get 28% towards the solution. And using search, we get 100%. Now, just to reiterate really quickly, search can actually find the solution 100% of the time, and depending on the search method, they can all find the solution 100% of the time. The thing is, and think back to the nQueens demonstration I showed you, when we use purely search, it's really inefficient, and so we don't want to use purely search. We want to use constraint propagation to narrow what we have to search, to narrow the search field. So anyways, with this small of a puzzle, we can actually do search just fine. But again, it's inefficient. And so looking here, we get these values, and these show us how far we get with each of these methods. And the start is 24. We start with 24 clues. Using weak propagation, we get to 33. Using constraint propagation, we get to 40. And using search, we get to 81. Of course, we get all of it. So now I'm going to go back to the code and explain exactly what's going on here. So here's our predicate difficulty. And difficulty takes a bunch of inputs. It takes 5 inputs. The first is our puzzle itself, the rows. That's pretty obvious. But then it takes these variables. And what these variables do is when instead of specifying a number or an integer and we specify a variable instead, we get to solve for that variable. So let's just go back quickly to length to explain what I mean exactly. So if here, instead of doing length rows 9, we did length rows x or something, then when we go to our query, we would output the value of the length of rows as x. It would say x equals 9, for example. But when we put 9 here instead, it's going to hold true when it's equal to 9. So basically, by having a bunch of variables here, we're defining these things that we want to find the values of. And that's why we need to put it in here. Now, at the start, we append all the rows. We covered exactly what that does earlier. And then we count the number of integers. So essentially what it's doing is it's taking all of all of the rows, concatenating them to one list so we can, and then we go down here, we go to count. And this method, I won't go into exactly the details. It's sort of like a loop or something. What it's doing is when it runs into an integer instead of an empty spot in memory, so basically if there's a clue filled in or if there's a number filled in, it counts it. If there's not a number, it continues on. So that's what count does. And we essentially are, and when we look back here, this is what we're counting. 24 is the number of clues at the start, and so on. We're counting those numbers, those integers, once after we've gone through a certain process. So the first one we do is just at the start. We want to measure how many clues do we start with. And then we define a bunch of different, these predicates which solve using certain techniques. The first one is weak propagation. And we do that, this is essentially the exact same as the solver, except instead of using all distinct, we're using something called all different. And all different is really similar to all distinct, but the difference is that it's only weak propagation. It can only do weak propagation, it can't do constraint propagation. And so again, think back to what I just explained, how weak propagation works. That's all it can do. Can't do more than that. And so basically it runs the solver the same way the solver runs, and then it just counts and it returns the number it finishes with, the count n. So n here. And now then we go to constraint propagation, and this is identical really to the solver, except there's no search. We use all distinct here, but after we count the number of integers we finish with filled in, and then we return that. And then finally we have search, and this is fail first search. I could integrate other search methods, but I just decided to do this one for simplicity's sake, pretty much. And again, we have a predicate really similar to the solver, except instead of having all distinct, we have we only use label. So we label rows and label columns. We don't use any constraint propagation. And again, this search can find solutions, but it just can't find them quickly all the time. And so this always works 100% of the time. And that's really pretty much it. So before I finish here, I just want to show a couple different puzzle examples and how we can use this predicate to compare difficulties and sort of get a better understanding of how our solving methods do with different types of puzzles. Alright, so I've inputted one other puzzle here, and this one I pulled from the easy section on the New York Times. And I haven't run this, so the result is going to be as much of a surprise to you as it is to me. So we're going to run this through the difficulty predicate and see what happens. Okay, wow, look. So as you can see here, when we plug in this puzzle, 100% of that puzzle can be solved using weak propagation. Weak propagation is really not all that efficient, or I mean, it's not all that good at solving these puzzles, but this puzzle is so easy we can do all of it just using weak propagation. And that really demonstrates how this difficulty predicate can be used as a really solid tool for determining how hard or easy Sudoku puzzles are. So I have written another puzzle here. This one I got from the Medium section on the New York Times website for today. And let's test this one and see how it runs through the difficulty. All right, really interesting. Okay, so as you can see, only 10% of this puzzle can be solved using weak propagation, but 100% of this puzzle can be solved using constraint propagation. Again, this is misnamed. Should be constraint because it's intelligent and weak combined. So this is like the example we saw a bit earlier in the video, which is that we can solve the whole thing just using constraint propagation. I think this is a really good way that the New York Times seems to define difficulty levels with puzzles. Easy puzzles should be able to be solved with mostly or purely weak propagation. Medium difficulty puzzles should be able to be solved with constraint propagation completely or almost completely. And the harder puzzles should be more oriented towards needing search. And these sorts of strategies, the terminology seems not to translate perfectly into how we solve Sudoku puzzles as humans, but as I explained earlier how each of these work, it's pretty much how we all go through Sudoku puzzles. The most beginners will see, oh, this can only possibly be a 7 in this square, so I'm going to put a 7. Those are beginners. Slightly more advanced people might say, oh, this is the only square in which 7 could exist, even though it could be an 8 as well. That's intelligent propagation. And then the hardest puzzles require a little bit more pattern finding, pattern skills, stuff like that, because you're going to have to make choices. You're going to have to decide and then, oh man, screw it up, and then go back and choose again. And so that is it for our program. That's it for our Prolog program. I think this is a really interesting lens into how AI problems are solved with Prolog, and a great example of that, as well as just a fun way to exemplify what we have learned about Prolog. And I think that the Sudoku puzzle itself, the solver itself, was fun, but it was really cool to sort of take an extra step, take a leap, and do this other predicate, which honestly gives us some really cool insights to difficulty levels and also just how these different solving techniques are used to solve these puzzles.